Hi folks, this is your second video on differentiation. This is differentiation by first principles. Now just as a recap from what you know from last year and higher, if I was to ask you to differentiate a function, let's say f of x equals x squared plus 2x plus 1, what we would do is use a rule for differentiation which says that f dash of x is going to be bring the power down the front to make it 2x and then subtract 1 from the power. So 2x, same thing again, 2x becomes 2 and then the 1 disappears. So we end up with 2x plus 2. Now, what we'll look at in advanced higher is where this idea, what differentiation actually is, and a different definition of differentiation. So I've got a graph here, a function here, and what I'm interested in is the derivative of this function, let's say at this point of x, which corresponds to that point on the graph there. Now bear in mind that when I ask for the derivative, what I'm asking is if I was to draw a tangent line to this graph, so I'll try that the best I can. So if I was to draw a tangent line like so, so it's a line that just glances the function at that point and that point only. When I differentiate, what I want to know is what's the gradient of that tangent. Now, to work out a gradient of a line, if you remember all the way back to National 5, the gradient of a line can be found by taking a vertical change over a corresponding horizontal change. Now, we're going to apply this same idea to this line that I've drawn here. However, in order to use this, I need to have a horizontal change, so looking at a single point is not actually that useful for me. So what we do is we make a gap. I'll do this in black. So let's say I make a wee gap here, and I say that the distance from x to that bit is just h. Just a letter we're going to use. So therefore the x coordinate here would be x plus h. So I've made a wee gap just so I can use this formula here, so a horizontal gap. Now if I just trace onto the graph what I get here, I'll try my very best to, what I get is like a wee narrow gap there on the x direction. Now what we're trying to do is make that gap as small as possible so that it just fits around this point that I care about, and then the tangent would go right through that. Now for the point x where it reaches the graph, the value of the graph, if I look over to the y-axis, remember the value of the graph you can think of as the height of the graph. The value of the graph at x would be f of x. And then for x plus h, this other point that I've made, if I trace that across, the value of the graph here would be f of x plus h instead. F of x plus h. So what I've managed to do is I've managed to make a wee horizontal gap, and I've managed to make a wee vertical gap that corresponds to that horizontal gap. And in that just surrounds the point that I want, and the tangent line's going right through that. Now the idea here is, I've kind of zoomed in on this quite a lot, but the idea is that this gap is as small as you possibly can make it. It's just big enough so that there is a gap, but it's minuscule, infinitesimally small. Now in this case, if I was to work out the gradient, i.e. the derivative, so I'll rewrite this as f dashed of x. Well, if it's the same idea as the gradient of this line, well, that would just be vertical over horizontal. So the vertical change here is f of x plus h subtract f of x, which would give me just the gap in there. So I'm taking the upper y value, subtract the lower y value, and that just gives me what's in between. So that would be f of x plus h subtract f of x. And that gives me a vertical change. Remember, these changes are really, really small. And that's all over. Well, my horizontal gap was h. We just called it h in this case. You can think of this as x plus h subtract h, which would leave you that wee gap, but we already called it h anyway. So just h. Now I'll put a wee asterisk against this line here, because remember what I said, that gap we're trying to make as small as possible. So we want to know what happens to this value, the value of this expression, as h gets smaller and smaller and smaller, gets towards 0. Now we have a way of doing that. If you remember from the previous video, we have a limit that will tell us that. So f dash of x, a better definition here would be it's the limit as that gap h tends towards 0. So as it gets closer and closer to 0, it gets smaller and smaller and smaller, of that expression we had, f of x plus h minus f of x all over h. And that there, and I've got a better example of it in the next slide, that is our new definition for the derivative, and that's the proper definition of what the derivative of a function is. Just bear in mind what it actually is, so it's just the vertical over horizontal again, basically, but this idea that the wee gap that we're making is getting as small as possible, is tending towards 0. So what we'll do is we'll do a couple of examples from your notes, just see if we can use this new definition for the derivative, this new definition to try and work out some derivatives. So example 1, we have f of x equals 6x and want to differentiate from first principles. So the first thing to do would be to state that, well, I know the definition of the derivative is the limit as h tends to 0 of f of x plus h minus f of x all over h. So that is the derivative. Now, next thing to state is that, well, f of x I know is just 6x, because it's telling me there, f of x is 6x. F of x plus h, however, is just what we get when we substitute in x plus h in place of x. So what we get is it's the limit as h tends towards 0 of, now if I substitute in x plus h into that function, I get 6x plus h minus f of x, which is just 6x, all over h. If I continue down to simplify that, so that's the limit as h tends towards 0. Now, if I can simplify this top line, so I can multiply the bracket, 6x plus 6h minus 6x all over h, and you maybe see where I'm going here. Continuing that down, the limit as h tends to 0, the 6x's will cancel on the top line, leaving me with just 6h. So 6h over h, which is really nice because the h's just cancel, and gives me the limit as h tends towards 0, h is cancelled, of 6. And in this expression doesn't have any h in it anymore, so the limit of that is just 6. There we go. And we can double check our knowledge of differentiation already, that if we differentiate 6x, yeah, we get 6 out, so that works out fine. Okay, so example 2, again another function now, 5x squared. I want to do this from first principles again. So first of all would just be to state the new definition of the derivative, f dash of x is equal to the limit as h tends towards 0 of f of x plus h minus f of x all over h. Okay, now same as before, we want to then just figure out what f of x plus h is and what f of x is. We know what f of x is anyway, so mainly just f of x plus h. And we get that by just substituting x plus h in for x. So this is the limit as h tends towards 0 of, that would be 5x plus h all squared minus 5x squared all over h. Continuing on, simplifying that top line, limit as h tends towards 0. Now that becomes 5x squared plus 2xh plus h squared minus 5x squared all over h. and continue to simplify. So limit as h tends to 0, 5x squared, and we'll see the 5x squares are going to cancel here, plus 10xh plus 5h squared minus 5x squared all over h. Continuing on, limit as h tends towards 0. 5x squared will cancel to give me 10xh plus 5h squared all over h. And I can cancel some h's there, so it's a limit as h tends towards 0 of that h will cancel. I'll just make that in red so you can see it. That h and one of those h's cancel with the h in the bottom. So that gives me 10x plus 5h. Now, at this point, this a fairly easy one now to work out. So like we saw before, we can just substitute our 0 in for h now, because this will be defined if we put h as 0 now. So the 5h becomes 0, and we get 10x. So that's 10x plus 5 times 0, which is just 10x. And again, using just looking at the start, 5x squared, if we were to differentiate it normally, power down the front, 10x. So 10x, happy with that. And the last example, f of x equals 4 over x. So again, just starting off with our definition, so f dashed of x is the limit as h tends towards 0 of 4 over x. Getting ahead of myself, f of x plus h minus f of x over h. Continuing on, so if I put x plus h into this, I get limit as h tends towards 0 of 4 over x plus h minus f of x is 4 over x, and that's all over h. Continuing on, so what I'm going to do in the top line there is combine the fractions just into one expression. So what we'd get would be 4x minus 4x plus h all over x times x plus h. That's the top line, and that's all over h. Combining that, now just bear in mind this line here is just h over 1, so if I'm dividing by h over 1, that's just the same as multiplying by 1 over h. So what I end up with is the limit as h tends towards 0 of 4x, and I'm going to multiply this bracket at the same time, 4x minus 4h all over h x plus h. Now just, you can take your time to go through from this second step here, have a wee think about what I've done. So getting a common denominator of x plus h, and then changing the numerators and adding them into one fraction. And then from this step, again, like I said, dividing by h over 1 is the same as multiplying by 1 over h. At this point, just a case of simplification, so limit as h tends towards 0, 4x's will cancel on the top, which is good, and we end up with negative 4h over h, and what I'll do is, I'll just multiply this out, hx squared plus h squared x. Okay, so we're getting closer now. You'll see again some h's will cancel, which will leave it quite nicely. So the limit as h tends towards 0, h cancels, so that's of negative 4 over just x squared plus hx. And at this point, this is at the point where you can just substitute in your h is equal to 0 and see what the limit is. So in this case, 4 is untouched at that point. X squared doesn't affect that either. However, the hx just goes to 0 if h is 0. Note that I don't get a 0 in the denominator's still going to be x squared, so that's perfectly fine. It's still defined at that point. So that is equal to the limit as h tends to... getting a wee bit ahead of myself there. So, apologies. Yeah, so like I was saying, I'm going to make h equals 0 to work out this limit. So that gives me negative 4 over x squared plus 0, which just is negative 4 over x squared. Okay, and if you were to try this, if you bring that up to 4x to the negative 1 and then differentiate it as normal, you get negative 4x to the negative 2, which is negative 4 over x squared. So that matches up, and I'm happy with that. Okay, so I suggest you just doing a wee bit of practice, understanding your limit, putting your expression into a form where you can substitute in your limit to work it out. So like in each of these cases, I didn't really want just this h on the bottom line because I would end up with something undefined. So in this case, I'm manipulating it so that it comes out quite nice and easy.